So here we go. So I got I got strict instructions that I needed to check better text writability mode, which I have just done. Okay, wonderful. Hopefully everyone can see these slides. I should just say my office here has been absolutely transformed into quite an elaborate recording studio here. You can't see it because it's off camera, but one of my cats has taken up residence on the power brick for the camera. So it's all quite different in here, but this is where I normally work. This is my office. And I'm delighted to be here broadcasting from South Kildare, where I live and work. So I'm going to talk to you about this topic, path dependence, and this sort of idea that history matters in various ways. And I guess the TLDR of path dependence, and we'll talk a lot more about this, is that this idea that that because of the order in which events occur and because of various constraints and the need for compatibility with other things, we can end up in these sort of local maxima where we're not in this optimal place where we could be and we're sort of stuck. And I think there's a lot of debate about whether this actually exists, but I kind of think it does. And so I'll talk about some ways that I think this plays out in technology. So first, who am I? I am not an astronaut, unfortunately. Although we're going to talk about space a little bit in this talk. This photo from me is from the Cité de l'Espace in Toulouse, in France. Highly recommend it if you are ever nearby. Toulouse is apparently not only about rugby and sausages, they also have an excellent space park. I'm a software engineer. I'm currently actually taking a bit of a career break from that because I am doing a master's degree in human factors and systems safety. I've worked in software engineering, and for the last 12 years, I've been more oriented towards performance and reliability and these sorts of non-functional things. And many SREs, site reliability engineers, have been very interested in various aspects of safety science. And so it's been very interesting for me to get the time to spend on that. And that's kind of where this path dependence topic comes in, as you're going to see. So a couple of other things I wanted to talk about. Aside from the masters, I keep busy with volunteering. I've done a fair amount of writing. I've listed some things there. I'm on the board of the Usenix Association. Some of you will have heard of SRECon. That's one of several conferences that we run, and I'm also one of the organisers of that conference. I liaise from the steering committee to the organisers every year. I also have done a bunch of curriculum design and volunteering and mentoring with a great organisation called Code Your Future. They're a UK-based organisation, and they work with disadvantaged groups, particularly refugees, asylum seekers. And we've done some great work with them building an infrastructure course, which sort of is geared towards getting people the skills to be productive in a infrastructure software team. And finally, I'm involved with the campaign to stop killer robots, which campaigns for a ban treaty against lethal autonomous weapons. I think most people who've seen how software is made in the real world are kind of appalled at the idea of letting the robots kill people. So that's a bit about me and where I've come from and what I do. So let's talk about path dependence. So as I said in the first slide, this is a concept that comes from social sciences, international relations, economics. It sort of crosses a bunch of different domains. Here's one definition that you'll come across, this idea that past events or decisions constrain later events or decisions. So because we did something, X years ago, a decision that we made, and in technology, this could be like a platform that we adopted or a programming language. This constrains in some ways the things that we do now. It can be business decisions that were made and so on as well. Then this other idea that is that what happens in the past persists because of resistance to change. We get into some pattern and it's hard to break out of it, even though there might be good reasons to break out of it. Then we have this other sort of sub-definition, which is that we have this tendency of organizations or technologies to develop in certain ways as a result of either their values or their structural properties. So something about the way that a technology is built has this sort of lasting influence, or something about the way that an organization has, something about its cultural history, or the constraints and pressures that it's under, have a lot to say about where it goes. And we have a great example of this coming up shortly. So I won't talk too more about this now. So as technologists, why is this relevant to us? And I think it is really relevant in a bunch of ways. So the first thing is we often want to create change in our organizations. We want to adopt some new kind of practice. So that could be site reliability engineering or DevOps or agile or test-driven development or whatever the new thing is. So we want to change how people work and change some mindsets. We need to get people on board and change ways of doing things. And this is, for anyone who's been involved in this or seen this done, will probably acknowledge that this is very difficult. And part of the reason for that is because cultures have durability. So things that elements of an organization's history or where it's been, they influence where you can go next. Not only where you are, but where you can go next. So you can have two organizations that kind of look like they're in exactly the same place, technologically or even culturally, but some elements of the ways that those organizations have developed can affect how people think and work in ways that make certain kinds of change more difficult or more easy. And I think that's really important to understand. Then properties of the systems that we build now can constrain what we're able to do in the future, or at least what we can do in the future at a reasonable cost. And I've got some examples of this coming up as well, and I think this is really relevant to what we do. Then system reliability, which obviously as someone who's done a lot of site reliability engineering is something I care about. System reliability is deeply bound up with all of this for the two reasons. So first off, path dependence can get us into positions where we're in this sort of local maxima, and we'd like to get to a place where things are radically different, but it's hard to get there from here. Or better reliability requires changing a culture in some way, and that's hard to do because of the durability of culture. So I kind of want to talk about our first sort of case study here next, because I think bringing things into a concrete case always helps a lot with making sense of the world. So I think this concept here is really what first sort of brings the idea of path dependence and history into safety science in a very concrete way, in a very sort of high impact way. So we're sitting here in 2024, and it's unbelievable to think that the Columbia Space Shuttle accident happened in 2003. That's 21 whole years ago. I remember it quite well, like it wasn't 21 years ago. But this was the accident which was caused by the shuttle's heat-resistant tiles being damaged on launch because of a piece of thermal foam that came loose from the booster assembly. Anyway, there was a very, very deep investigation into that incident by a group called the Columbia Accident Investigation Board. And the report they produced is freely available on the internet, and it's a really interesting read. It's really high writing quality, amazing information, very, very good reasoning and arguments. This is astronaut Dr. Sally Ride. She was part of the Columbia Accident Investigation Board, and she had also been part of the accident investigation process for the Challenger accident, which happened in 1986. The Challenger accident occurred as a result of two O-rings, redundant O-rings in the solid rocket booster mechanism, and they failed. It was cold. They were not as able to block the path of gases, and unfortunately, Challenger broke up just after launch. But Sally Ride, around about the start of the Columbia investigation, she was the first to say that the Columbia accident had echoes of Challenger. And that was kind of an interesting comment to make, because at the technical level, the mechanisms of these accidents were really different. There were totally different subsystems involved. One accident happened on launch, the other accident happened on re-entry. Superficially, there's sort of nothing really to relate these accidents. So what did Sally Ride mean? So to talk about that, I'm going to jump back a little bit and talk about this book and the person who wrote this book. So this book is the Challenger launch decision, and this is sort of one of the core texts for this degree that I'm doing out at Lund, the Human Factors and Systems Safety. And it was written by Diane Vaughan, who is a sociologist, And she wrote this book in 1996, about 10 years after the Challenger accident happened. And it's a really great read. You know, I know sociology and a really great read are rarely juxtaposed in the same sentence, but I think it's a great read. Prior to Vaughan, the received view about Challenger was that the cause was the O-rings, and the failure of the O-rings to contain those hot gases in the cold weather, combined with NASA management's disregard of concerns brought to them by engineering because of launch pressure. So the story was O-rings failed. Engineers had expressed concern. They had this very 11th hour, very high stress kind of teleconference that they did literally the night before the launch, where they were discussing whether or not this should go ahead. This is quite an unusual event around these launches. Like, it wasn't normal to have this kind of "will we do it" conference right beforehand, like raising this specific kind of technical issue. But they did, and what happened in the end was that the managers basically said, hey, if we don't launch tomorrow, when will we launch? We have all these delays, we really want to launch. So they went ahead and they did it. But there was more to the story than just managers throwing their weight around and managers being subject to production pressure. Vaughan adds like a huge amount of nuance to the story. One chapter is purely an account of the pre-launch meeting and how the actual decision making happened, and that chapter will have you on the edge of your seat, even though it is sociology. But Vaughan adds these kinds of ideas which deepen the understanding of how that decision was made. And the first concept is normalization of deviance, which is something that those of us interested in reliability may have heard of. It's the idea that we can get used to events happening that we know aren't supposed to be happening according to the design of the system. And we see ourselves getting away with these kinds of events. We see that, okay, we have maybe a little brownout, we drop a few requests, but the system recovers, so this is fine. So it would be an example from our world. In NASA's case, they were frequently seeing this gas blow by on the O-rings. They were seeing the O-rings being charred when they recovered that stage of the rocket and inspected it afterwards. So they knew this was happening, but they got used to it. They stopped thinking about it as a safety risk, and they sort of got used to it. They were like, we have seen this before, it's never caused an accident, so why should we be so concerned about it now? So a similar process happened with Columbia, with the foam. From the second launch of the shuttle program, they were seeing these foam strikes, and they were seeing damage to these heat tiles. And again, they sort of got used to it. They normalized that deviance in the same way that they did with the O-rings. So this is sort of a process that plays out through history. You get used to these things because the history of these events has shown that they're harmless, even though they're not harmless. They're sort of forewarnings of risk. Vaughan also argues really strongly that one of the real sort of root cause, if you will, of the accident actually stemmed from the shuttle program's history. So basically the political and the budgetary decisions that were made about the program created structural conditions and pressures at NASA that set the stage for flawed decision making, which led to both those disasters. So Vaughan writes this chapter on the Columbia report, where she writes about those systems properties that she thinks caused the accidents, with different technical causes, but the common organizational ones. So the story is that after the Cold War, NASA was much less of a budgetary priority in the US than it had been during the Cold War, during the Apollo program, the moon landings. So when the shuttle program was conceived, it had to pay for itself cost-wise, or at least it had to claim it would pay for itself. It never did. So the idea was that it would maintain a high frequency of launches, and it would bring all sorts of payloads up into orbit for all sorts of different parts of the U.S. System. So military surveillance and so on. And so NASA had to sort of start thinking like a business, and sort of start bringing the cost and efficiency pressures and schedule pressures onto an equal footing with safety and with technical innovation. So now they have limited budgets, which is different. So as a response to that, to save money, they do more outsourcing. That makes it hard to communicate clearly about risks, and it's very much a direct consequence of the budget pressure. This also means that they have to choose which kinds of issues to prioritize. So in the case of the O-rings, do they prioritize that issue over other things that are cropping up from time to time? And likewise with the tiles, things have to sort of make it to the top priority list in order to get actions. And I think this is something we all understand. We all work in contexts where we have all sorts of budgetary and schedule and production pressures. So as a result of these pressures, NASA and the schedule pressures and the cost pressures, NASA has to, in order to operate, has to normalize flying with flaws. And those constraints basically guarantee disaster at some point. You can't know what particular launch is going to cause a problem, but what you do know is that at some point you're going to have an issue. So another sort of element of history that fed into this was that NASA had this very much a can-do attitude, very much left over from the moon program, where they were under this incredible pressure to get things done, but they also had basically infinite budget and resources. So they always figured out a way to get there. And the shuttle program operated under this very different set of circumstances, but it sort of retained that attitude. And so they ended up doing crazy things like cannibalizing one shuttle to make parts to launch another shuttle, stuff like this. And all of these pressures did ultimately turn into disaster. So that's kind of my first example of path dependence, the sort of the role of history in these major complicated incidents. So let's jump back a little bit and look a bit more at the definition of what path dependence is. So this comes from, again, this concept comes from all sorts of different parts of theory. So social sciences, international relations, economics, and they all have slightly different views on it. But this view is from the economist side. So Stan Leibowitz and Stephen Margulis, who are kind of critics of path dependence. So definition one is durable decisions. Things we do in the past constrain us in various ways in the future, even just because it's expensive to replace things that we've already done. Their example is you buy a house. That's a fairly durable decision because it's expensive and inconvenient and takes a lot of time and effort to move house. So you may buy a house and then you may find that your situation's changed. You need more space or less space, or something higher cost or might be appropriate now, or something lower cost. But every time your circumstances change slightly, you don't buy a new house because it's so awkward. So you might deal with a long commute, or you might deal with having your home office in the dining room. If there's a pandemic, you don't just move straight away when something happens. So I think this is kind of the definition that the Columbia Accident Investigation Board were using, although they have all these cultural elements as well. They had these durable and hard to undo decisions were made early in the shuttle program about the shuttle's design, and those sort of led those compromises. And these were things like not having a bailout system for the astronauts in the event of a disaster, for example, was one of those decisions that was made. Those are hard to undo later on because you have this incredibly complex design that you've built. And so there's a bunch of factors here that can make things durable. So durability of capital equipment, and I think this probably also would include durability of, say, complex code bases as well. Then you've got technical interrelatedness. So if you make a decision to build on top of some piece of infrastructure and that becomes sort of very much entwined with your code base, it's, again, hard to undo that. And then, second decision that we have is decisions made with imperfect information, where we make a suboptimal decision because we don't have a perfect oracle of the future. So an example here is what if we buy a house and then the next year a sewage plant gets built next door. We probably might not have chosen to buy that house if we knew that there was going to be a sewage plant. So we have this inefficiency that occurs because we fail to predict the future perfectly. And then those decisions might not be efficient or optimal in retrospect later on. So I think this exists in technology as well. So here's an example I'm going to give. So HHVM, this is Hip Hop Virtual Machine. It's a VM that runs hacklang programs. Hack is an evolution of PHP, which is used with HHVM. It was open sourced by Facebook, as was, now Meta, in about 10 years ago, in sort of the mid-noughties. It was originally basically a faster way to run PHP, but the language diverged, and now HHVM cannot run regular PHP anymore. And it was a really interesting thing that happened. Like when HHVM came out and kind of made this, quite a splash, and a bunch of organizations kind of jumped over to using it, as it was at the time significantly faster than PHP. Problem is, if you're still on HHVM, you have had to switch over to use hacklang rather than regular base PHP. And that means you're kind of stuck on HHVM. Now you have this very big switching cost if you want to go back to regular PHP. And HHVM is very much focused on Meta's needs. I'm aware of organizations that are using it, and they have some considerable pain because while HHVM is open source, all of the internal libraries and tooling that Meta use with it internally is not, and that can cause some problems and gaps. And then things like there's very little support for things like, say, Postgres database, because HHVM is used at Meta, which is very much a MySQL shop. So there's sort of problems there. And then the other thing that happened was, partly as a response to HHVM, mainline PHP just got a lot faster, and it has much better tooling if you're outside of Meta. So hack users outside of Facebook are left kind of high and dry. It's, they're reliant on this project that's very much controlled by Facebook, has minimal open source info other than what Facebook uses, minimal kind of IDE tooling support compared to regular PHP. So yeah, I think that's an example of Leibowitz and Margolis's second type of path dependence. So effectively, the hacklang users have kind of built their VM beside a sewage plant, which is not great. This is, I think, a durable decision made with imperfect information. So they have a third definition, which is decisions that and this is really interesting to me, decisions that we make, and at the time we know they're inefficient, they're not the best system that we could have, but it's what we do because of the need to coordinate with other actors. And this, according to Leibowitz and Margolitz, is the strongest form of path dependence. So they think it means that you have inefficiencies that don't have to be inefficient. So their example here is, that a sewage plant is going to be built, but you build your house beside it anyway because all of your friends are buying houses in that area. Maybe it will be a better world if you and all your friends bought a house somewhere else, but you can't convince all of your friends to move away en masse. You're unable to coordinate. So this is the kind of the strongest claim that we make suboptimal decisions for this reason. And this to me brings to mind IPv4 and IPv6. So I think if we were, building the internet from scratch right now, knowing what we know, we would not build IPv4. It's not really fit for purpose. What we have is an internet built of kludges and top of kludges and more kludges. And we ran out of IPv4 address space years back. We would do something different. And IPv6 is the solution that has been proposed. 1998, the draft standard was published, and it's been a full-fledged standard now for a few years. But it's really impractical. You can't run on only IPv6. Maybe you can do it for internal sort of private clusters, although there's still a whole bunch of annoyances with this. But it's just, you couldn't set up a cloud provider and say, okay, we're IPv6 only. The internet is still primarily IPv4, and I think it will be for the foreseeable. I mean, are we stuck with it forever because of path dependency? We have to use IPv4 because everyone uses IPv4. One of the strongest examples of the idea of path dependence is this idea of railway gauges, and there's been a lot of studies done on this. Um, so most of the world's railway gauges, these sort of long distance heavy rail, is 4 feet 8 inches or 143.5 centimeters. This is called standard gauge. Despite the fact that most engineers will tell you that wider gauges are better performance, better speed. So the reason for the 4 foot 8 gauge is in the 1820s, a guy called George Stephenson, he was an engineer, and he was working on railways in Liverpool and Manchester. And his previous experience had been with coal tramways, which used quite a narrow gauge for good reasons in that application. And so he picked that gauge for that reason. So there are trade-offs involved. Having a wider gauge increases the cost of the line, but various performance metrics get better as well. Maximum speed, lower center of gravity, and so on. There was an attempt to introduce a thing called the Brunel gauge, which failed, and a bunch of other gauges, which also failed. But you know, these gauges they failed because of a lack of because it's really awkward when you have a gauge break in a railway network. So primarily for interrelatedness reasons, a lot of these railways that picked a different wider gauge ended up going to the standard Stephenson gauges, and this is called the break of gauge problem. It's really interesting. When railways started out, a lot of the railways sort of kind of said, well, you know, railway will only ever be a local thing. We'll just have this little network that will interconnect these few towns here, and everything will be great. So they weren't even thinking about having, you know, broader interconnected rail networks, even in a country or even between countries. So so it sort of reminded me of those days where, you know, people were saying, well, you know, we'll maybe need, what, 6 or 8 mainframes for the whole world. This is fine. So anyway, railways are sort of, railway gauges specifically are seen as one of the best and strongest examples of this path dependence idea. The critique of the path dependence concept basically says, well, hey, I mean, railways are the only really good case that we have of this. There are a couple of other cases that people very often present, one of which is the QWERTY keyboard layout. People say, oh, Dvorak is better. It turns out that the evidence for Dvorak being better is maybe not as strong as it could be, and so there's a whole debate around this. The other one is VHS format, videotapes versus Betamax, which God, how to even explain this to the young people? old video technologies before we had YouTube, and a bunch of people say, well, actually, Betamax was better, so why did VHS win? But other people point out that VHS let you record longer pieces of content than Betamax did, so that might be a good technical reason why it was that VHS eventually won out, even if Betamax had better quality, perhaps. So a lot of people sort of argue against QWERTY and Betamax as examples of path dependence. So on to kind of culture change stuff, which I think a lot of us have grappled with or have seen other people grappled with. So a friend of mine, I swear, this is not me, a friend of mine runs a reliability organization in a good size sort of unicornish tech company. And a few years back, when she started doing this, people were reluctant to attend their post-incident review meetings and were reluctant to present them. And this was, you know, because of the way that the culture of this organization was at the time. People felt there was a blameful culture, and people were reluctant to stick their head over the parapet. So for quite a while, my friend basically ran it this way. So managers who had incidents would run a review in their team, and they would give my friend the report, and she would present that to the rest of the organization and the executives. And the managers of those teams would still attend so they could clarify any matters and make sure that their teams were well represented. So this worked fine for a while, but over time, managers stopped attending the meeting because they developed such a trust in my friend that she would accurately and fairly represent them. But then that's not good because the managers aren't there and there's no mechanism for people in different parts of the organization to learn from each other's incidents. So because of the way that this has all developed along this path, my friend has now had to stop presenting the incidents and go back to having the managers present them themselves. And that now works fine, whereas it didn't a few years ago, because there's the trust that there's a fair and a blame-free culture. So you have to adapt what you do to where you are, and not just where you have been, if that makes sense. And sometimes you can get to the place that you want to be, but not directly. I think adopting site reliability engineering mindsets and practices is another example of this. People very often say, you must introduce SLOs, this is the first thing that you do. And it's been really popular as a concept in the past 6 or 8 years. And yes, SLOs are useful. I will not argue against having SLOs, but if you turn up at an operations org that's kind of underwater and on fire, yes, you can be underwater and on fire at the same time. I've seen it. With loads of manual work, lots of noisy alerts, and you say, the first thing that we require is an SLO project. People will not thank you because there's no immediate, obvious payback for them. So you can do other smaller things that can help immediately, and you can use other tools like a regular production meeting where people will talk about their recent experiences and concerns, in order to understand how things are and identify some pain points you can fix short term. Then you can build some trust, build a bit of breathing space, and then maybe think about your SLO project. So, because the dirty secret of SRE is many SRE initiatives fail, and I think this kind of very one-size-fits-all approach is a big part of that. I think Kubernetes and the way that orchestration has moved in the last few years is also an interesting thing to think about in the context of path dependence as a concept. So I think it's been pretty widely acknowledged for the last 4 or 5 years that Kube has won the container orchestration wars. So whereas things like Nomad and Docker Swarm and Mesos have not. Kubernetes support is now basically universal in the major cloud providers, and there's a lot of tooling providers now, and a whole ecosystem like Helm charts and specific libraries of Helm charts you can use, operators, and so on. So I think this is has become one of these situations where as a tool provider, or as a user, targeting any other ecosystem, you have significant disadvantages. Although I will put off to the one side and say that I think there's very much still a niche for simpler cloud projects like ECS. If you have a small team without a lot of operations capability and you don't need the complexity, like that's very, very much still viable. But for the orgs that need a full-fledged container orchestration solution, I see very, very, very few people going to anything other than Kubernetes. But Kubernetes didn't have first mover advantage, which is quite interesting. So Mesosphere was out a lot earlier than Kube. There's no kind of railway gauge effect here. Although the cost of moving your orchestration framework is probably less than that of regauging your railways, which is very expensive. Kube had more features built in than most of the other orchestration solutions, so it includes affordances for things like service discovery and ingress load balancing and things like that. It had the support of Google and CNCF, so those are seen as kind of stabilizing forces. And there was a timing issue. I think Kubernetes sort of hit at a time where a lot of organizations were moving on to their first ever orchestration framework. So it wasn't that a lot of people moved away from Nomad and Docker Swarm, it's that they were doing this for the first time and they said, okay, Kubernetes seems like the way to go. But it's a very strong incumbent now, and I think any challenger would have a hard time replacing it. So this is something we might. I'll put a reminder to revisit this in 10 years and see if I was right. Terraform is another quite interesting example. So again, it's another software infrastructure example. This is what I know the best, but it's been very dominant in infrastructure configuration management for quite a few years, despite efforts like Pulumi and now Crossplane. And also many vendor-specific tools, like all of the big cloud vendors have their own thing, like CloudFormation is Amazon's one, which have tried to do the same thing as Terraform and maybe unseat it. I feel like this might be an example of path dependence because there's a lot of Terraform code out there, and porting it would be a pain. Not to mention people know the tool. There will be operational aspects of, changing your build pipelines and all these things, or your deployment pipelines. But God, everyone hates Terraform. I mean, most people hate Terraform anyway. I mean, it's awful to write complex modules. I love a ternary operator. My first proper programming language was C, but I don't like ternary operators for everything. And will Terraform prove to be the IPv4 of software infrastructure? I don't know. Maybe it'll be like PHP was when HHVM challenged it, and we have this taking some of the characteristics of the competitors. So what we see is after Pulumi, which aims to solve the same problem but using regular programming languages instead of declarative HCL. What we see is Terraform have now come out with this Terraform CDK, which is again more programming language oriented. So maybe what we see is this evolution in the incumbent rather than being unseated or seeing a real sort of diversity spring up in the space. So that's interesting. Okay, so moving towards the end of the talk, I have some takeaways. I hope people have had lunch already. So the first takeaway is making durable decisions is important. Durable decisions are the ones that are going to constrain you down the line. These are the decisions where it's really worth taking the time to make sure that you've thought through what you think will happen, and also maybe what is your worst case scenario. If something doesn't go the way you expect, so for example, HHVM doesn't catch on broadly in infrastructure or in the industry, are you going to be left high and dry in some way? So there's things like, which programming language to choose, which cloud to run on, which database to use. These are fairly durable decisions. Adding layers of abstraction is actually a durable decision as well, because we only ever add layers. You can never remove a layer of abstraction, almost impossible. So it's good to do experiments and spikes and really think hard. API design can be this way as well. If APIs are quite sticky, it's hard to turn them down. So yeah. Then I think it's a concept we can use in incident reviews. It's so we saw how the Columbia Accident Investigation Board really took the concept that history had fed into this incident in various ways quite seriously. And a lot of organizations now are doing post-incident reviews, and we tend to focus very strongly only on the technological aspects, but I think sometimes it's interesting to think as well about how history has fed into how things unfold, because if we look only at the technical aspects of our systems and we ignore the whole human side of what's going on, and this is what the resilience engineers call the above the line, below the line framework, we kind of miss half of what's actually going on in our systems. So I think thinking about the path dependence aspects is very interesting. Example of this, I worked somewhere once that tended to have a lot of incidents linked to deploys that went bad, and this organization did very fast releases all the time. So things would go from PR submitted to in production fully within a few minutes. And I always thought that we did not give enough time for soaking changes at a canary stage. But this culture had it's the ingrained culture of this organization valued speed at all costs, and sort of, I think, implicitly was okay with having a relatively high number of availability incidents as a result of being very, very fast with releases. What that organization was not good at, I think, was articulating that trade-off to themselves. They kind of wanted both sides, but that's difficult to do. So I think if we really wanted to fix those problems, we would have had to grapple with that culture issue. So the final sort of takeaway is, when you're trying to do something, ask if you can get there from here. Or at least, can you get there directly from here? At any given point in time, an organization has been on a journey, and there are certain things that you can do next, and certain things that you can't. You would need to do something intermediate, and you need to move in stages. So think about that example of the teams and their post-incident reviews, and whether the managers present or not. And so if we're trying to make some kind of change and failing, maybe this is the reason, and we need to think about some sort of intermediate point that you can set your course for. So that's it. That's the talk. And I believe we're going to do Q&A for a few minutes next, if there are any questions.
To cup of tea, need a 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 cup of tea, need a